Hello, it is I, Mr. Burkhart, here with another exciting edition of Mr. Burkhart Talks About the Answers for the workbook. All right, let me go ahead and hit my stopwatch and go find the answers. There they are. Angela is going to shake her hand in the rope and get a continuous wave. A graph of the wave is shown at right. And so label the crest, the trough, the amplitude, and the wavelength. So on a wave like this, which is called a transverse wave, you'll find that you have up bumps, which are like maxima on sine curves. In math class, those are called crests. It's a vocab word. And on the bottom, you have an equivalent piece, which is called a trough. They're really the same thing, just one's up and one's down. One's got a positive amplitude, one's got a negative amplitude. And the amplitude is a measure from rest to crest or rest to trough. The wavelength is the measure from one part of the wave till the next identical part of the wave. So you can go from tip to tip. Here they're going from the point of inflection to the next point of inflection. I think when you did your lab, a lot of people didn't understand. You need to go through the whole, you need to have a whole cycle to get the period or to find the wavelength. And sometimes you're only going to have a part of one. Your graph may only show half of a wavelength or whatever, not a full wavelength. On the diagram below, sketch a continuous wave with half the amplitude. And with half the amplitude is Angela shaking her hand with 5 times per second. The wavelength is 1 meter. Calculate the speed. Okay, so there's the amplitude. Basically, it's the same wave as Angela's wave. It's just going up to 3 instead of 6, or going down to -3 instead of -6. You can see it's basically got the same wavelength and same period. Continuous wave with twice the wavelength. So you can see here, and we have the same amplitude. We're going up to 6 on the y-axis, but now the wavelength, instead of the wavelength being 10 units, now it's 20 units on the graph paper. So when they calculated, I'm sorry, I skipped the part where we calculated the speed. They did the wavelength, which is 1 meter, times the frequency, which was 5 hertz. How did they get that? Oh, it was given 5 times per second is 5 hertz. So wavelength times frequency is the same as distance over time, distance over period. So that'll be 5. All right. Is Angela shaking the string at the same rate when? I don't know. Same rate to get the last continuous wave. To make the wavelength longer, the frequency must decrease. And I don't know, I think you are shaking the slinky slower, giving it a slower frequency to get more wavelength. And that's what it says here in the words. Must shake the slinky slower, string slower to create a longer wavelength, but the same rate box is checked. That doesn't make any sense. I don't know what to say. Okay, you are given a long length of string and an oscillator that can shake one end of the string at any desired frequency. So it's like a thing that can go like basically some sort of machine that can make the string flop up and down. So you can imagine a string tied here, and it's going to make the string go. The oscillator has a display that indicates frequency. How convenient. You're going to design an experiment to determine the velocity of a standing wave in a string. All right. So what I'm thinking is you get the thing going, and it tells you the frequency. So that's one thing you need. The other thing you need is the wavelength. So you're going to have to figure out some sort of experiment for measuring the distance between 2 fixed points. And then that is the wavelength. And then you can just, it looks like they're going to keep repeating that so you can get different harmonics, which we haven't talked about what a harmonic is yet. And so we would analyze the data, the distance L to calculate the wavelength, divided by or times the frequency would give us the speed. So here's the following data. Here's some sketches of different harmonics. So basically what we'll find is that when you have a medium, it will resonate or oscillate at specific frequencies. And it's just kind of this discrepant quantum phenomena that happens. And so you can see the first one, the fundamental harmonic, it's half of a wavelength because it doesn't go through a whole up and then a down. It's just one up, and then you can see that it's reflecting. And so we're kind of getting ahead of ourselves. Actually, we are not really ready to talk about this stuff, but that's okay. I guess we're going for it. I don't remember. This feels like this is next week's curriculum, but whatever. So if you just look at the thinking of the bottom as a reflection of the top, it's a half a wavelength. And then the next harmonic, you get a full wavelength. You get the, it's reflecting and going back on itself. And that's why it creates these mirror image shapes. But it's got one whole cycle, and then you get three, and then you get, so 3 halves of a wavelength, and you get 4 halves of a wavelength, and you keep going, and it just keeps creating these harmonics, odd and even harmonics is what they're called. And then here is the graph of the data, the frequency versus the inverse of the wavelength gave us a slope. And that's going to give you the speed. So nice lab. I'm still in part B. Yay. In 6 minutes. Or was that just part A? I don't know. Okay. I might as well finish up B. These drawings represent snapshots taken of waves traveling to the right along strings. The grids shown in the background are identical. The waves all have the same speed, but their amplitudes and wavelengths vary. Rate the frequency of the waves. Okay. They're saying B is the highest frequency, and that's because the little points are closest together. So high frequency means short wavelength, which means since they all have the same medium, they all have the same speed. So short wavelength, high frequency. So B, and then A would be the next one. And then you can see D is greater than C. Boy, that is really hard to tell, honestly, from those two graphs. I might have said that C was actually greater than D. Its amplitude is different. Really hard to tell for me personally. I think they're really being picky there. But you can see they did have an explanation. All right, let's stop the video because we're at 7 minutes.